Hello everyone, again so welcome back to our latest lecture session. So we are hopefully going to wrap up precipitation and dissolution in this session. So one of the last aspects that we are going to look at is the predominance area diagrams. As we briefly touched upon or discussed them in the last session, right, we say that we are going to look at a summary of the relevant scenario, right, or a snapshot of the relevant scenario. And this is going to be useful, let's say, when you want to obviously get a generic idea of which species will predominate at which particular pH or which particular scenario, right, or at which particular set of conditions. So I guess one example we are going to have or look at is, let's say, the acid-base speciation for H2CO3, HCO3 minus and CO3 2 minus. Okay. We know that, let's say, if this is the concentration and this is the pH, you know that the true picture would be something like this, right. So this would be the H2CO3 concentration, which would decrease with pH, right, and this would be the HCO3 minus concentration, HCO3 minus concentration, and this would be your, or let's say this would be your CO3 2 minus concentration, right. Yes, and we know that these points of intersection, when both the relevant variables are equal, will be the pKa1 and pKa2, right. So, but obviously, you know, if I want to get at the predominance area diagram, what is it that I am going to represent? I am going to represent that region in which that relevant compound is going to be at higher concentration, right, or is going to predominate. So obviously the graph that we had earlier is going to transform into something like this, right. So what is it that we understand? This is the pKa1, this is pKa2, right. So when pH is less than pKa1, what variable or which compound is going to predominate? H2CO3, and obviously that is what you see here too, right. When pH is less than pKa1 or in this region, which particular conjugate acid or base in this particular system is predominating, you see that it is H2CO3, right, and that is what we have here, right. And obviously this solid line, what does that represent? That represents that the concentration or that region where H2CO3 concentration is equal to HCO3 minus, right. So that is the key here, that the solid lines represent that particular region when the, and this solid line obviously would represent the region when HCO3 minus is going to be equal to CO3 2 minus. And where do you know that these occur? This will occur at pKa1 and this will occur at pKa2, right, and that is what you see here. So again, from this particular graph, the predominance diagram, right, you know that HCO3 minus, or this tells us that HCO3 minus will predominate between the pH of 6.3 and 10.3, and let us look at the graph that we have earlier, and that is what we see here, right. Between pKa1 and pKa2, even though you have HCO3 minus or CO3 2 minus, which is the variable or compound that is going to predominate, it is HCO3 minus, right, and that is what we have here. And similarly, when pH is greater than pKa2, you know that CO3 2 minus is going to predominate, and that is what you see here, right. So again, keep in mind these predominance area diagrams give a snapshot, right, not the true picture, as in you do know that between pH of 6.3 and 10.3, while HCO3 minus concentration is relatively higher, right, it does not mean that there is no H2CO3 nor no CO3 2 minus, right. As you know, near let us say pH 7, you still have some H2CO3, and near pH 10, let us say, you will still have CO3 2 minus. So keep in mind that these what is it now, predominance area diagrams give a summary, right, or obviously a snapshot of what variable, or pardon me, which compound or what compound predominates, but that does not mean that there are no other compounds present in that particular region, right. So in general, again, you know, they give a snapshot, that is the key. Keep in mind that they do not give a true picture of the relevant equilibrium related species concentration, right. So let us say now we are going to move on to one particular example which we did earlier, when we had both CaCO3, the solid, and the CaOH twice, the solid, right. So we looked at one particular graph, right, where I think for log total C and with respect to pH, right, and log CO3 total, I believe, right, we came up with graphs as in this region, right, and CaOH twice would be this, and we say that in this region CaCO3 is going to predominate, right, and this is when Ca2 plus is in equilibrium with CaCO3, and this is when Ca2 plus is in equilibrium with CaOH twice, because in this region this particular variable is less than this variable, CaCO3 solid is going to precipitate, and in this region, right, CaOH twice is going to precipitate, right. So, but obviously let us say if I want to get a snapshot of what is happening in the system, I need to be able to draw what now or develop what? I need to be able to develop the boundary lines. So, let us just try to develop those boundary lines, right. So, obviously how can I develop the boundary lines, or when will both the solids precipitate out, right? When the concentration of calcium in equilibrium with CaCO3 is going to be equal to the concentration of calcium in equilibrium with CaOH twice, right. So, as in what is that region? Obviously this is the region, right, we are trying to look at, and now I am going to say how, or try to figure out how it varies with pH, right. So, that is what we are going to try to plug in, and I guess we looked at this particular equation in the last class, so I am not going to write that down again, but I think its case solubility product of CaCO3 was equal to the K star, right, of CaOH twice, right, into I think H plus square, right, into CO3 2 minus, that would mean alpha 2 into CO3 total, right. This was the relationship I believe we figured out when we were trying to look at the relevant what we say case when both the solids would precipitate out. So, this was the equation, and obviously when would that be the case? When the concentrations of calcium that would be in equilibrium with both the solids, they are going to be equal. So, now I am going to have to figure a way out of coming up with or breaking this down into sections where for a particular pH this is the solid that is going to predominate, and for a particular pH which is the solid that is going to predominate, right. And let us see how we can go about that. So, obviously for a given CO3 total, right, or these two are constants, the solubility product of CaCO3 and the modified solubility product for CaOH twice, they are constants, yes. And for a given scenario CO3 total 2, this let us say is a constant for a given scenario, right. So, what obviously changes here? You see that alpha 2 will change with pH, right. So, keep in mind that in this equation you can see that alpha 2 is going to change with pH, and we know that alpha 2, what is that? That is nothing but CO3 2 minus by CO3 total, right. But we also know we can express that as what is it now, K1 K2, right, by H plus square plus H plus into K1 plus K1 K2, right. This is alpha 2, and K1 K2 obviously are those acid dissociation constants for H2CO3 dissociating into HCO3 minus and H plus. The K1 would be for this equation, K2 would be for the second acid dissociation equation, right, HCO3 minus reaction, pardon me, would be in equilibrium with CO3 2 minus and H plus, right, K1 and K2. So, we are just trying to refresh our memories. These are aspects that we have covered in great detail in our acid and base relevant process, right. So, we know that alpha 2 is going to be this particular case, right. So, now I am going to look at 3 cases, right. The 3 cases are going to be when pH is less than pK1, pH is less than pK1, right, and we know that pK1 means it is 6.3, and when the pH lies between pK1 and pK2, and the third case obviously when the pH is greater than pK2, right, pH is greater than pK2, and pK2 we know is around 10.3. So, for these 3 cases we are going to work out the relevant equation, and you will see how it makes sense now with respect to understanding the predominance area diagram, right. So, let us go through with that. So, the first case is when pH is less than pKa1, right. So, that is what we are going to work out now, right. So, obviously alpha 2, right, what will it transform into in this case when pH is far less than pK1, right. So, alpha 2, right. So, K1 K2 is going to be K1 and K2, but which term would predominate here in the denominator now when the pH is very less? Obviously H plus concentration is going to be very high. So, this particular term is going to predominate, as in alpha 2 is going to be equal to K1 K2 by H plus square when the pH is less than pK1, right. So obviously keep in mind that we are making some approximations here, right. So alpha 2 is going to be equal to K1 K2 by H plus square. So I'll plug this in into my equation here, right. So now what do I end up with now, I guess, right. I'm going to have KSO CaCO3 will be equal to K star CaOH twice, right, into H plus square into alpha 2 is now K1 K2 by H plus square, right, into CO3 total, right. So, or I can also express this obviously as CO3 total is equal to K solubility constant CaCO3 by K star CaOH twice, right. H plus square and H plus square obviously cancel each other out, right, and CO3 is total. So, I am still going to have what else please here, I am going to have 1 by K1 K2, right. So, what does that more or less turn out to be? So, if I take log, right, log CO3 total would be equal to log of this particular set of variables, right, and as you see this is a constant, right. So, what does that mean? When the pH is less than pK1, right, there is no dependence upon pH, that is what you see here, right. Is there any pH relevant aspect in this particular what do we say now, equation? None, right. So, what does that mean? That region, when the pH is less than pK1, right, the predominance area diagram or the relevant relationship when CaCO3 and CaOH twice precipitate does not depend upon the pH, right, in that particular variable again. So, it is going to be a straight line there, I guess. So, keep that in mind. So, next aspect is obviously when part B, when I guess pH, right, is between pKa1 and pKa2, right. So, obviously in this case what will alpha 2 turn out to be? We know alpha 2 was equal to K1 K2 by H plus square plus H plus into K1 plus K1 K2, right. So, obviously in this particular scenario we know that alpha 2 is now going to be equal to K1 K2 by, so which term is going to predominate? Obviously H plus into K1, right, H plus into K1, right. So, plugging this in into that relevant equation and so on. So, we will end up with obviously CO3 total will be equal to KSO CaCO3, right, by K star for CaOH twice, right, and this is similar obviously to what we have out here, right, out here or the transformation here, right. So, we are going to have that in, and obviously it is now going to be equal to what else now please. So, H plus square, we still have H plus square, right, into what do we have here? We have K1 K2 by K1 K2, or this is obviously going to be equal to K2 by H plus, right. So, K1 K1 cancel out and this is what we have. So, this obviously is now going to be equal to K2 by H plus, right. So, one H plus and H plus here can cancel out. So, if I take the logarithm, what is that going to be equal to please? Log CO3 total will be equal to the log of KSO CaCO3 by K star CaOH twice, right, by, is it going to be by K2 into H plus or by K1 K2 by H plus square here, right. So, I guess I should have written that down in the different manner here. So, it would have been H plus by K2, right, into 1 by H plus square, right. So, obviously because I am bringing this term out here to the left hand side. So, that is going to be H plus by K2 into 1 by H plus square. So, that is obviously going to be equal to 1 by K2. So, this again is a constant, right, and here we have logarithm of H plus to the power of minus 1, right. So, negative logarithm of H plus. So, what does that mean? We know that pH is equal to minus log concentration of H plus, right, and that is what we are left with here. So, it is going to be plus pH, right. right. So now it's going to be, this is the constant that we had earlier, not the same one, by K1, K2 I guess, right. And now we also have plus pH. So in the region when, what is this now, pH is between 6.3 and 10.3, you know that the relevant boundary when CaCO3 and CaOH twice both precipitate will increase linearly with pH, right, with increase in pH. Again, once we draw the diagram, it's going to be relatively clearer. So the next case is going to be C, when pH is greater than pK2. What does that mean? That means alpha 2 is going to be equal to, we are looking at this. So obviously which particular term will predominate here? K1, K2 will predominate in the denominator, right, and that means obviously alpha 2 equal to K1, K2 by K1, K2, right. That means alpha 2 equal to 1, right. So obviously I am going to plug that in here, and CO3 total is going to be equal to KSO CaCO3, right, by K star CaOH twice, right, into what else do you have here? I have 1 by H plus square, right, and alpha 2 is 1, so 1 by alpha 2 will be 1, right. So now if I take the logarithm of this particular equation, what do I end up with? So log CO3 total is equal to log of this particular variable here, right, and what else do you have? Log of 1 by H plus square, right, and again we know that it's going to be equal to minus 2 log H plus if I take log of 1 by H plus square, right, and that is nothing but equal to plus 2 pH, right. So it's going to be log CO3 total equal to log of this particular set of variable plus 2 pH, right. So now the slope, right, is going to increase. So earlier when pH was less than pK1, there was no effect of pH. When pH was less than pK1 and pK2, increases with pH, and here when pH is greater than pK2, we see that it increases with the rate of 2 times the pH. So let's look at this in terms of the relevant graph, right. So here is the graph that we have. So initially you see that, you know, when pH is less than 6.3, right. So when pH is less than pK1, which is this region, right, and if you look at the relevant equations that we came up with, we saw that it was a constant, right. For a particular log total C, we saw that it was a constant, and let's just try to go back to that graph or the equation. So this is what we had, right, the relevant relationship. So log CO3 total was log of a particular constant, right. So for a particular CO3 total, the boundary was constant, I guess, right, and that's what you see here. And for the second case, you saw that we had a particular additional term, as in for log CO3 total, we had something like log of some constant plus pH, right, and that was the case when pH was between 6.3 and 10.3. So that is why you see this particular increase, right, the slope, right, when the pH is between 6.3 and 10.3. This was for case B. And for case C, if you remember, we had something like log CO3 total is equal to log of some constant, right, plus 2 times pH, right. So obviously the slope is going to be greater, and that is why you see that when pH is greater than pK2, which is 10.3, as in this region, right, what do you see? That the slope is higher, right, so the slope is greater. So what do I understand from this particular aspect now, right? So keep in mind that we were discussing the predominance area diagrams, right, and we were trying to draw the relevant predominance area diagram between CaCO3 and CaOH twice, the solids. So what does this mean now? When, let's say, in this particular region that we see here, we see that CaCO3 is going to predominate, right, and in this particular region here, or beneath this particular line, you are going to see that CaOH twice is going to predominate, right. So that's what we understand from this particular system. So obviously what does this particular solid line indicate? It means that at that particular solid line, right, relevant to that particular log total CO3 or pH, both the solids are going to precipitate. Makes sense, hopefully, right. So in this region, again let's try to understand this. When the log total C is higher, or CaCO3, right, the solid we know is in equilibrium with Ca2 plus and CO3 2 minus, right. So when log total CO3 is higher, it means that in general relatively CO3 2 minus concentration is higher, right. So obviously what does that mean? This particular backward reaction would be feasible, as in more of the CaCO3 would be formed, leading to less Ca2 plus, as in CaCO3 would predominate. So that's why you see that at higher log total CO3, CaCO3 is predominating, right. But obviously again we know that CaOH twice, this solid is going to be in equilibrium with Ca2 plus and 2 times OH minus. So at higher pH, right, at higher pH you know OH minus concentration is going to be higher, and then this backward reaction is going to be relatively more favorable, leading to formation of CaOH twice. So that is why you see that as the pH keeps increasing, right, you see that CaOH twice, right, would precipitate out rather than CaCO3 at the given conditions of the log total CO3, right. Makes sense hopefully, yes. Again, so this will obviously try to help you understand the system. So obviously at remarkably high pH, right, so for most values of log total CO3, right. So for example, let us say I take this particular value of log total CO3, right. So you know until let us say pH of around 8.3 looks like CaCO3 is going to predominate, and from 8.3 and higher looks like CaOH twice is going to predominate, right. So that is what we understand from the system. So now let us say, but in this case, right, what is it that we have here? We see that, right, we consider that the solid is always formed, right, but will that always be the case? Not really though, right, because sometimes you will have undersaturated solution. This is what we talked about earlier, I guess, right, we talked about saturation ratios and such. So when the relevant concentrations of the metal or the cation and the anion are not high enough, what do you see though, right, you see that the solid will not precipitate out, right. So you will have those cases, right, when you might have no solid precipitating out. Here we are looking at in this graph, this predominance area diagram, we are obviously considering that we either have CaCO3 or CaOH twice always. So what is the missing picture here? We are missing the picture where we have the undersaturated regions, right. So again we can set that up in the relevant equations and calculate that, which we are not doing here, but I have the relevant graph here, right. So let us look at what we have here, I guess, right. So here we have a new term or variable, here we also have Ca2 plus. So obviously what does this mean now in this region, right, it is undersaturated, right, with respect to your precipitation, let us say, right, and Ca2 plus is the what do we say, would predominate out, right. So obviously as you keep increasing the pH, right, so at lower pH and at lower log total CO3 you see that Ca2 plus would predominate, but and that is obviously in this whole region, right. So when this region would correspond to relatively low pH, right, as you see here, and relatively low log total CO3, right, and that is what you would expect to, right. But as you keep increasing the pH, right, what do you see now? Ca2 plus 2 OH minus, you know, are going to be in equilibrium with CaOH twice, right, and that is why as you keep increasing the pH here for a particular log total CO3, you see that in this region CaOH twice is going to predominate, right. But obviously let us say for a given pH, if I keep increasing the log total CO3, what do I see? Let us say in this region, right, I see that CaCO3 predominates, yes. So again keep in mind that at lower pH and at lower log total CO3, right, as in we have two ways that Ca2 plus can precipitate out, right, that is with CO3 2 minus, right, as CaCO3 or CaOH twice, right. So at either lower pH, meaning OH minus is less, or at lower log total CO3, meaning CO3 2 minus is less, obviously it is going to be, which reaction is going to be favorable now? The dissolution, this solid will not be favorable, right, and that is why you would see relatively high concentrations of Ca2 plus in these regions, right. And obviously as you see that the pH is increased, right, as you see that the pH is increased, right, and you will have this particular equation predominating as in the backward reaction, that is why CaOH twice, and same case out here, right. So again I guess with that we are more or less you know about to be done with our particular case, right. So in general again keep in mind predominance area diagrams give you a snapshot, right, as in when we solve the example, especially with respect to that H2CO3, HCO3 minus and CO3 2 minus, you see that it gives you that particular area when that particular variable or compound is going to predominate. That does not mean there are not going to be any other compounds present. So, in general I will always suggest, when you want to go for detailed calculations or such, you use Vmintech, or obviously try to solve it by hand, or use your intuition that you would have or should have developed by now, right. So, I guess one particular aspect that we will talk about before ending this particular session with respect to what is this now, precipitation and dissolution, is going to be the Langmuir saturation index. So, we have a Langmuir saturation index, right, and I guess this is going to be equal to pH minus pHs, right, and that pHs is that particular pH which would be in equilibrium with Ca2 plus for a given alkalinity, right, yes, and for CaCO3, right, when equilibrium is reached for a particular alkalinity, right, and between CaCO3 and Ca2 plus, and that particular pH would be the pH at the saturation value, I guess, pHs, I guess, right, and saturation index is calculated as pH minus pH s. So, when this is positive, that means the situation is oversaturated, right, and when it is equal to 0, it is nowhere, I guess, right, it is just saturation, and when it is negative, it means it is undersaturated, right. So, again, what is pHs? That pH at which for a particular concentration of alkalinity, right, Ca2 plus and CaCO3 would be at equilibrium, let us say, right, pHs. So, obviously, when pH is greater than pHs, what does that mean now? It is oversaturated and it will precipitate out further, right, or CaCO3 will precipitate out, and obviously, if it is undersaturated, that will not be the case. And people look at this, what is it now, the saturation index or Langmuir saturation index, let us say, to understand if the system can precipitate out or system can lead to precipitation of CaCO3 or not. And why do people look at this? Let us say, because sometimes let us say in your distribution networks, right, you are going to end up having corrosion, let us say, right. So, but let us say if you maintain the pH at the relevant value, you will have a protective layer of CaCO3 formed, as in let us say if this is your what do we say, cross section of your distribution pipe, let us say, and let us say if you have a layer of CaCO3 scaling on your particular surface of your distribution system, right, if you maintain the pH at a right value, not too high, then when you are going to have blockage or decrease in the effective cross section area, but let us say when you maintain the pH at a sufficient value, let us say, which is oversaturated, you will have precipitation of CaCO3 on the what we say, surface of your particular pipe, and that will act as a protective film or cover. Anyway, that is one particular case when people try to maintain this particular pH, right. So, I guess with that I am done with precipitation and dissolution. So, now we are going to move on to the redox process, right, which are ever present, yes. So, for now we will have a brief discussion for, I guess, a couple of minutes regarding what these redox processes are and why they are relevant to us, and then we will go on to move into more details in the next particular session, right. So, now we are going to move on to redox process, right, redox or reduction and oxidation, right. So, let us just again try to summarize what we have been up to until now, right. So, initially we looked at the basics for any chemical process, that would be equilibrium, as in how far the system can go to under specified set of conditions, right, and kinetics, as in how fast will the system go, I guess, right. And in that particular aspect we looked at until now 3 major aspects, right, and what were they? We looked at acids and bases, and then we looked at aqueous complexes, right, and also we looked at precipitation and dissolution. And in all these aspects we then looked at mostly applications of equilibrium or kinetics. We know that in acids and bases kinetics are very high, so that is why we end up only discussing obviously equilibrium. Same case in aqueous complexes, kinetics is very high, so that is why again we mostly looked at only the relevant aspects with respect to what the system would be after equilibrium has reached, right. Again, if the kinetics are so high, right, by usual what do we say, time frames you look at, you would obviously reach equilibrium. That is why we obviously only looked at equilibrium, right. But with precipitation and dissolution, we know that precipitation reactions can be relatively slow, especially from amorphous to crystalline to more insoluble forms. So we also discussed kinetics and obviously equilibrium in that particular case. So with this we were done, I guess, right? But as you remember, in one of the classes we did mention that all these cases there is no change in the oxidation state or oxidation number, right, of the relevant what do we say, element here, right? But here now we are going to have redox reactions, right? Redox reactions, right, when there is going to be a change in your particular oxidation state of this particular compound or the element. Again, we are going to discuss this in the later classes. But keep in mind that all these three aspects that we have covered thus far, right, are coordinative relationships, right, which is not the case with redox process. But one aspect with redox process, I guess, that I think we need to cover, or I am not sure if I use this particular example, I think I did in one of the initial classes, was that, right, if I have, I think I did, right, you know, if I open up, I know that, let us say, you know, C6H12 O6 plus, I think, the oxidation, right, you know, it can go to the relevant products, I think CO2, H2O, and a lot of energy. I think delta G was negative, right, but this does not give me an idea about the energy release and plus heat, right. Delta H will give me an idea about that. I think delta H2 is negative and it was considerably high, right. So I guess C6H12O6, let us say glucose, let us say, right, or let us say if I open up a packet of glucose and throw it out here, or let us say, you know, open up a you know, toffee bar or coffee bar and throw it out, you know, it is not going to lead to explosion or nobody is going to run away from here, right. And I think obviously the explanation was that even though considerable amounts of energy are going to be released, it is the time that's required, right, for time it takes for that energy to be released, that's the key. Unlike an explosive that people use, let us say, right, this particular what do you say, C6H12O6 does release considerable energy, but over a considerable period of time. So here what I am trying to stress upon is that unlike the relevant aspects we discussed as far as in aqueous complexes or acids and bases, you know, kinetics play a remarkably important role in the redox reactions. So rarely do you have most systems reaching equilibrium, but almost all of them are going to be dependent upon, highly dependent upon your kinetics. So whenever someone talks about redox reactions, it is the kinetics that play a remarkably important role, right, and rarely do they reach equilibrium. I mean, some of the reactions can reach equilibrium, right, but keep in mind again that we can understand equilibrium to see, you know, if it reaches equilibrium, what would be the relevant what we say changes. But the key is that will we ever reach equilibrium given the certain conditions or such. So we always need to look at kinetics with respect to the redox process, any redox process, I guess, right. Again, that is one particular aspect that I guess I need to highlight. So over the class or over the next remaining sessions, we are going to talk a lot about kinetics, and then we are going to talk, I guess, about you know, what would happen, let us say, if the system reaches equilibrium, or what would the system look like, I guess, right. But again, keep in mind redox process, again, every time it is the kinetics that plays an important role, right. So in this aspect, again, why do we need to look at redox process, or where are the general applications, I guess, right. I guess I or you are a living example. I am taking in oxygen. Again, why is that for now? You know, you are eating food, right, and again, what's it more or less now? It's an oxidation reaction, right, of the sucrose that you are going to digest or such, right. It's again an oxidation reaction, and you are going to release energy from that oxidation reaction, which I am going to use for either my cell synthesis or growth, or, you know, my bodily functions, right. Again, I am breathing in oxygen, taking in oxygen, a source of oxygen, and it is going to help in oxidation of the relevant sucrose or glucose, right, and that is going to lead to release of energy, right. Again, that is a redox process, oxidation of the relevant glucose or sucrose or the relevant compounds, right. At a macroscopic level, I guess, I am sure there are relevant what do we say, reactions, right, between what do we say, you eating food and you ending up getting energy, but let us say that is one particular way to understand what happens in the system now, right. So again, let us see where else we come across this redox process. You know that activated sludge process, or let us say sequential batch reactors, or blah blah, again, that you use for your treatment of your organic compounds or your waste, right. So again, what are the key factors that you are usually putting in here, let us say. So let us say this is my ASP, right, and this is my secondary settling tank here, let us say, right, and this is the recycle here, and this obviously is the inlet here, let us say, right. So here in this activated sludge process, this particular tank here, right, which is always well mixed, right, and what else are you supplying now? You are always supplying a source of oxygen, right. So why is that now, right? And you also have organic compound here, which is the waste that you are trying to degrade, right. So organic compounds are usually the reduced forms or in the reduced forms, right. And why are you supplying oxygen? Because you want to oxidize this particular organic compound, right. And obviously this is the relevant reaction here, right. So this is the organic compound which is relatively in the reduced form, right, and you are going to supply oxygen, and the microbes, right, they are going to act as catalyst. The enzymes released by the microbes, they are going to act as catalyst to make this particular redox reaction go through faster. So if there were no microbes, let's say, right, it's going to take remarkable amount of time, the kinetics is going to be very slow, right. But obviously the role of the microbes, right, they are going to assist in this particular process. Why is that? The energy that's released, the microbes are going to use for either their cell synthesis or cell growth, repair, and so on, right. So same case as us, they too want to derive the energy that's going to come through based on this particular degradation or oxidation of your waste or the organic compound. Again, why are we using microbes? Because we want to fasten this process, which would otherwise take considerable or practically impossible or infeasible amounts of time, right. So the microbes here play the role of catalysts, right. They fasten this particular process, and why do they want to do so? Because they want to use this particular energy for themselves, right. And again, keep in mind that the applications of redox reactions, obviously here I gave a generic example of where you would come across redox reactions, right, but maybe people do not play as important a role as you should. But obviously again redox reactions are ever present, right. In the atmosphere, yes, any particular, what do we say, transformations, that not any, most of them are redox processes again. Or let's say you take a bite of an apple and leave it out exposed to the atmosphere. Now what do you see? You see exposed layer of the apple turning brown. What's happening there? You see that Fe2 plus, right, is going to be oxidized. Anyway, this is not a balanced reaction to obviously to Fe3 plus, right. So whenever you bite an apple, leave it out, right, and what do you see? The iron there, it's, I believe, going to be oxidized to Fe3 plus, right, and that's what you see there, the brownish color change, right. So again, there are multiple applications, or redox reactions are ever present everywhere, right. Let's say if I am trying to degrade a compound, let's say chlorinated organic, let's say RCl, right, usually they are toxic or carcinogenic. Now I want to degrade that, so what do I need? This is a oxidized compound, right. So I need to add a reducing agent. Again, we are going to see what these reducing agents are or so on, so that I can oxidize this or reduce this particular contaminant, right. So again, with that I am going to end today's session, and we are going to go through redox process in great detail over the next sessions. And I guess with that I am going to end today's session, and thank you.